The Sun's environment is many occasions more sizzling than its surface. Here's when. The noticeable surface of the Sun, or the photosphere, is around 6,000 degrees Celsius. However, a couple thousand kilometers above it, a little distance when we think about the size of the Sun, the sunlight-based environment, likewise called the crown, is many occasions more blazing, arriving at 1 million degrees Celsius or higher. This spike in temperature, in spite of the expanded separation from the Sun's principal fuel source, has been seen in many stars, and addresses a major riddle that astrophysicists have thought about for quite a long time. In 1942, the Swedish researcher Hannes Alfvén proposed a clarification. He hypothesized that polarized floods of plasma could convey gigantic measures of energy along the Sun's attractive field from its inside to the crown, bypassing the photosphere prior to detonating with heat in the Sun's upper environment. The hypothesis had been probably acknowledged, yet we actually required evidence, as exact perception, that these waves existed. Our new examination has at last accomplished this, approving Alfvén's 80-year-old hypothesis and making us a stride nearer to outfitting this high-energy wonder here on Earth. The coronal warming issue has been set up since the last part of the 1930s, when the Swedish spectroscopes Bengt Edlund and the German astrophysicist Walter Grotrian originally noticed wonders in the Sun's crown that must be available if its temperature was 2 or 3 million degrees Celsius. This addresses temperatures up to multiple times more smoking than the photosphere underneath it, which is the outside of the Sun that we can see from Earth. Assessing the photosphere's warmth has consistently been generally clear. We simply need to quantify the light that contacts us from the Sun, and contrast it with range models that anticipate the temperature of the light's source. Over numerous times of study, the photosphere's temperature has been reliably assessed at around 6,000 degrees Celsius. Edlund and Grotrian's tracking down that the Sun's crown is such a great deal more blazing than the photosphere, regardless of being further from the Sun's center, its definitive wellspring of energy, has prompted a lot of head-scratching in established researches. The limit warmth of the Sun's crown is quite possibly the most vexing issues in astronomy. Researchers look to the Sun's properties to clarify this dissimilarity. The Sun is made for the most part out of plasma, which is profoundly ionized gas that conveys an electrical charge. The development of this plasma in the convection zone, the upper piece of the Sun-oriented inside, produces colossal electrical flows and solid attractive fields. These fields are then hauled up from the Sun's inside by convection, and burble onto its noticeable surface as dim sunspots, which are groups of attractive fields that can shape an assortment of attractive constructions in the Sun-powered environment. This is the place where Alfvén's hypothesis comes in. He contemplated that inside the Sun's polarized plasma any mass movements of electrically charged particles would upset the attractive field, making waves that can convey gigantic measures of energy along immense distances, from the Sun's surface to its upper environment. The warmth goes along what are called sun-powered attractive motion tubes prior to blasting into the crown, creating its high temperature. A graph of the Sun's various highlights. Sunspots are more obscure patches on the Sun's surface. Siberian art, Shutterstock. These attractive plasma waves are presently called Alfvén waves, and their part in disclosing coronal warming prompted Alfvén being granted the Nobel Prize in Physics in 1970. Noticing Alfvén waves. In any case, there stayed the issue of really noticing these waves. There's such a lot of occurring on the Sun's surface and in its environment, from marvels commonly bigger than Earth to little changes beneath the goal of our instrumentation, that direct observational proof of Alfvén waves in the photosphere has not been accomplished previously. Yet, late advances in instrumentation have opened another window through which we can look at sunlight-based material science. One such instrument is the interferometric bidimensional spectropolarimeter, IBIS, for imaging spectroscopy, introduced at the Dunn Solar Telescope in the U.S. territory of New Mexico. This instrument has permitted us to mention undeniably more nitty-gritty observable facts and estimations of the Sun. Joined with great review conditions, progressed PC reproductions, and the endeavors of a global group of researchers from 7 examination establishments, We utilized the IBIS to at last affirm, interestingly, the presence of alpha-N waves in Sun-based attractive transition tubes. New fuel source. The immediate revelation of alpha-N waves in the Sun-powered photosphere is a significant advance towards misusing their high-energy potential here on Earth. They could help us research atomic combination, for example, which is the interaction occurring inside the Sun that includes limited quantities of issue being changed over into enormous measures of energy. Our present thermal energy plants utilize atomic parting, which pundits contend produces perilous atomic waste, particularly on account of fiascos including the one that occurred in Fukushima in 2011. Making clean energy by recreating the atomic combination of the Sun on Earth stays a gigantic test, since we'd in any case need to produce 100 million degrees Celsius rapidly for combination to happen. Alpha-N waves could be one method of doing this. Our developing information on the Sun shows it's positively conceivable, under the correct conditions. Understand more. Nuclear combination. Assembling a star on Earth is hard, which is the reason we need better materials. We're additionally expecting more Sun-powered disclosures soon, because of new, pivotal missions and instruments. The European Space Agency's Solar Orbiter satellite is presently in circle around the Sun, conveying pictures and taking estimations of the star's strange polar areas. Presently, the divulging of new, elite Sun-oriented telescopes are additionally expected to improve our perceptions of the Sun from Earth. With numerous mysteries of the Sun still to be found, including the properties of the Sun's attractive field, this is an energizing time for Sun-powered investigations. Our identification of alpha-N waves is only one commitment to a more extensive field that is hoping to open the Sun's excess secrets for functional applications on Earth.